Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the summer of 1950, physicist Enrico Fermi posed a question that would haunt humanity for decades. Where is everybody? This simple inquiry, made during a casual lunch conversation at Los Alamos National Laboratory, crystallized one of the most profound mysteries in science, the Fermi Paradox. Consider the numbers. Our Milky Way galaxy contains roughly 400 billion stars. The observable universe stretches across 93 billion light-years, encompassing an estimated 2 trillion galaxies. Even the most conservative calculations suggest that billions of Earth-like planets exist within the habitable zones of their stars, where liquid water could persist on planetary surfaces. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to quantify the probability of extraterrestrial civilizations. This equation multiplies the rate of star formation by the fraction of stars with planets, the number of habitable planets per star system, the fraction that develop life, the fraction that evolve intelligence, the fraction that develop detectable technology, and finally, the length of time such civilizations remain detectable. Even using pessimistic values for each variable, the Drake equation suggests thousands of technologically advanced civilizations should exist in our galaxy alone. Yet we detect nothing. No radio signals, no megastructures, no obvious signs of galactic engineering projects. This absence of evidence creates the paradox that bears Fermi's name. The silence becomes more puzzling when we consider the age of the universe. At 13.8 billion years old, the cosmos has provided ample time for civilizations to arise, evolve, and spread across vast distances. Our own solar system formed only 4.6 billion years ago, making it relatively young compared to many stellar systems. Civilizations could have had billions of years head start on humanity. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. The search for extraterrestrial intelligence, or CTI, has monitored the cosmos for artificial signals since the 1960s. Projects like the Arecibo Observatory's observations and the Breakthrough Listen initiative have scanned millions of stars across multiple wavelengths. These efforts employ increasingly sophisticated technology, analyzing petabytes of data for patterns that might indicate intelligent origin, yet the electromagnetic spectrum remains eerily quiet. We find no obvious techno-signatures, no industrial pollutants in exoplanet atmospheres, no artificial lights on the dark sides of distant worlds, no massive engineering projects blocking starlight in regular patterns. The universe appears devoid of the technological fingerprints we might expect from advanced civilizations. Some researchers argue we may be looking in the wrong places or for the wrong signals. Perhaps advanced civilizations communicate through quantum entanglement, gravitational waves, or technologies we cannot yet imagine. Maybe they deliberately avoid detection, practicing a form of cosmic stealth to prevent interference from younger species like ourselves. The James Webb Space Telescope and other next-generation instruments promise unprecedented sensitivity in detecting atmospheric biosignatures and potential technosignatures around nearby exoplanets. These observations may finally break the great silence, revealing whether Earth represents a cosmic anomaly or part of a universe teeming with hidden life. The Fermi Paradox forces us to confront uncomfortable possibilities about our place in the cosmos. Are we alone? Are we early? Are we looking in the wrong direction? Or does something prevent civilizations from reaching the stars, creating a filter that few species survive? Understanding this paradox may determine not just whether we find alien life, but whether humanity itself has a future among the stars. The Great Filter Hypothesis, proposed by economist Robin Hanson in 1996, offers a chilling explanation for the Fermi Paradox. This concept suggests that somewhere between the emergence of life and the development of galaxy-spanning civilizations lies an evolutionary barrier so difficult that virtually no species successfully passes through it. The filter could operate at multiple stages of development. Perhaps the transition from non-living matter to self-replicating organisms represents an almost impossible leap. On Earth, abiogenesis, the process by which life arose from organic compounds, occurred approximately 3.8 billion years ago, yet we still cannot replicate this process in laboratories despite decades of research. The fossil record reveals numerous mass extinction events that nearly sterilized our planet. The Permian-Triassic extinction 252 million years ago eliminated 96% of marine species and 70% of terrestrial vertebrates. The Cretaceous-Paleogene extinction 66 million years ago ended the dinosaurs' dominance. Each event represents a potential filter that could have permanently ended complex life on Earth. The evolution of eukaryotic cells, organisms with nuclei and organelles, took roughly 2 billion years after life first appeared. This endosymbiotic revolution, where one cell engulfed another to create mitochondria and chloroplasts, enabled the complexity necessary for multicellular life. The rarity of this event in Earth's history suggests it might represent a significant filter. Intelligence itself may be evolutionally expensive and rare. Human-level cognition required specific environmental pressures and evolutionary pathways that might be extraordinarily uncommon. The development of language, abstract thinking, and technological manipulation represents a convergence of traits that evolution does not inevitably produce. Even if intelligence emerges, the leap to spacefaring technology presents formidable challenges. Civilizations must master nuclear physics, rocket propulsion, life support systems, and interstellar navigation while avoiding self-destruction through warfare, environmental collapse, or resource depletion. The window between achieving destructive capability and developing space-based redundancy may be perilously narrow. Nuclear weapons represent humanity's first test of the Great Filter. Since 1945, we have possessed the ability to render our planet uninhabitable. The Cold War brought us to the brink of extinction multiple times, with incidents like the Cuban Missile Crisis and the 1983 Soviet early warning system malfunction nearly triggering global thermonuclear. War. Climate change presents another potential filter. Industrial civilizations inevitably alter their planetary atmospheres through energy production and resource extraction. The ability to recognize and mitigate these changes before they become irreversible may distinguish successful species from those that collapse under their own waste products. Artificial intelligence development poses unprecedented challenges. The creation of superintelligent systems could represent either the solution to cosmic expansion or the ultimate filter. Civilizations that fail to solve the alignment problem, ensuring AI systems remain beneficial to their creators, might be eliminated by their own technological creations. The Kardashev scale, developed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy consumption. Type I civilizations harness their planet's energy. Type II civilizations capture their star's output, and Type III civilizations utilize entire galaxies. Humanity currently ranks as a Type 0.7 civilization, still dependent on fossil fuels and unable to control planetary energy flows. The transition between Kardashev levels may itself represent filter points. Building Dyson spheres or similar megastructures requires unprecedented coordination, resources, and technological stability. Civilizations might regularly fail these transitions, collapsing back to pre-technological states or going extinct entirely. Recent research suggests the Great Filter might lie ahead of us rather than behind us. The absence of detectable alien civilizations could indicate that technological species regularly fail to become spacefaring, succumbing to challenges we have yet to face. This possibility makes understanding and navigating potential filters crucial for humanity's long-term survival. Perhaps the universe teems with intelligent life, but advanced civilizations deliberately maintain their invisibility. The zoo hypothesis, first articulated by MIT radio astronomer John Ball in 1973, proposes that Earth exists within a carefully maintained preserve, observed but not contacted by superior intelligences, who follow strict non-interference protocols. This concept draws inspiration from human wildlife management practices. National parks protect ecosystems by limiting human intrusion, allowing natural processes to unfold without technological interference. Similarly, galactic civilizations might establish zones where younger species can develop independently, free from the disrupting influence of advanced technology and alien contact. The technological gap between a spacefaring civilization and pre-spaceflight humanity could be so vast that direct contact would prove catastrophic. Consider how European contact devastated indigenous American populations through disease, cultural disruption, and technological displacement. An alien civilization, even centuries ahead of us, technologically might inadvertently destroy human society through mere contact. Advanced civilizations might possess technologies that render them effectively invisible to our detection methods. Kardashev, Type II civilizations, capable of harnessing stellar energy through Dyson spheres or similar megastructures, might engineer these constructions to appear as natural phenomena. What we interpret as stellar variability or unusual spectral signatures could actually represent camouflaged alien technology. The concept of technological transcendence suggests that sufficiently advanced civilizations might abandon physical reality entirely, uploading their consciousness into computational substrates or exploring higher dimensional spaces invisible to three-dimensional observers. These post-biological entities might observe the universe through means we cannot detect or comprehend. Communication protocols between advanced civilizations might operate on timescales incomprehensible to short-lived biological species. While humans measure significant events in years or decades, million-year-old civilizations might communicate through processes spanning millennia. Our radio telescopes might be listening for signals transmitted on temporal scales we cannot perceive. The prime directive, popularized by the Star Trek science fiction franchise, but based on serious xenobiological considerations, proposes that ethical space-faring civilizations avoid interfering with the natural development of pre-contact species. This principle recognizes that technological gifts or cultural contact could fundamentally alter a species' evolutionary trajectory, potentially preventing unique developments that emerge through independent growth. Observational studies of human behavior might be conducted through methods that leave no detectable traces. Advanced sensor technologies could monitor Earth from distances measured in light years, using gravitational lensing, quantum entanglement, or exotic physics we have yet to discover. Automated probes no larger than dust particles could provide comprehensive surveillance while remaining completely undetectable. The Sentinel hypothesis extends the zoo concept by proposing that monitoring systems throughout the galaxy automatically enforce non-contact protocols. These artificial intelligences, possibly created by long-extinct precursor civilizations, might suppress any attempts at interstellar expansion by younger species, maintaining cosmic stability through active intervention. Some researchers suggest that alien contact has already occurred, but remains hidden from public knowledge. Government agencies might possess evidence of extraterrestrial visitation, but maintain secrecy to prevent social disruption, economic collapse, or religious upheaval. The gradual disclosure movement argues for slowly introducing humanity to alien reality through carefully managed revelation. The watershed moment theory proposes that civilizations face specific tests that determine their readiness for cosmic citizenship. Nuclear weapons development, climate change mitigation, artificial intelligence alignment, or other technological challenges might serve as examinations administered by watching alien observers. Only species that successfully navigate these crises earn the right to join galactic society. Recent developments in exoplanet detection have identified thousands of potentially habitable worlds within our galactic neighborhood. The Kepler Space Telescope and Transiting Exoplanet Survey satellite have revealed that Earth-sized planets in habitable zones are remarkably common. If the zoo hypothesis is correct, many of these worlds might harbor developing civilizations. under similar protective protocols. The implications of the zoo hypothesis are both comforting and disturbing. While it suggests we are not alone and may eventually join a cosmic community, it also implies that our development is being monitored and possibly controlled by entities whose motivations and methods remain completely opaque to human understanding. The rare Earth hypothesis, developed by paleontologist Peter Ward and astronomer Donald Brownlee in their landmark 2000 book, argues that while simple microbial life might be common throughout the universe, the specific conditions required for complex multicellular organisms are extraordinarily rare. Earth's ability to support intelligent life may result from an improbable convergence of cosmic circumstances that few planets experience. Our planet's location within the Milky Way's galactic habitable zone provides the first crucial advantage. Too close to the galactic center, and lethal radiation from supernovae, gamma-ray bursts, and the central black hole would sterilize planetary surfaces. Too far from the center, and heavy elements necessary for rocky planet formation become scarce. Earth orbits within the narrow galactic ring, where stellar metallicity enables terrestrial planet development while avoiding catastrophic radiation events. The Sun itself represents an unusually stable star. As a G-type main sequence star, it provides consistent energy output over billion-year timescales, avoiding the violent flares common in red dwarf stars or the short lifespans of massive blue giants. The Sun's position between spiral arms means it avoids regions of intense star formation that generate dangerous radiation bursts and gravitational disruptions. Earth's orbital characteristics create additional rare advantages. Our planet maintains a nearly circular orbit at precisely the right distance to keep water liquid on the surface. The gravitational influence of Jupiter acts as a cosmic vacuum cleaner, deflecting potentially catastrophic asteroids and comets away from the inner solar system while not being so massive as to disrupt Earth's orbit through resonance effects. The Moon's presence may be essential for complex life's development. Our unusually large natural satellite, formed through a Mars-sized impact early in Earth's history, stabilizes the planet's axial tilt and creates tidal forces that may have facilitated the transition from marine to terrestrial life. Without lunar stabilization, Earth might experience chaotic climate variations that prevent long-term biological evolution. Plate tectonics represents another potentially rare planetary feature crucial for life's sustainability. The movement of crustal plates regulates global temperature through carbon cycling, prevents atmospheric stagnation, and creates diverse environmental niches that drive evolutionary innovation. Many rocky exoplanets might lack the internal heat sources or proper composition necessary to maintain active tectonics over geological timescales. Earth's magnetic field, generated by its liquid iron core, shields the atmosphere from solar wind, erosion, and protects the surface from harmful cosmic radiation. Mars lost most of its atmosphere after its magnetic field weakened, demonstrating how quickly planetary habitability can be compromised. The specific conditions that maintain Earth's geodynamo may be uncommon among terrestrial planets. The development of oxygenic photosynthesis represents a biological innovation that might be extraordinarily rare. For 2 billion years after life's emergence, Earth's atmosphere contained virtually no free oxygen. The evolution of cyanobacteria, capable of splitting water molecules and releasing oxygen as waste, fundamentally transformed planetary chemistry, enabling complex multicellular life, but also causing the first major extinction event as anaerobic organisms died en masse. The late heavy bombardment, which occurred approximately 4 billion years ago, might have been necessary for delivering water and organic compounds to Earth, while not being so intense as to sterilize the planet completely. This delicate balance between destructive impacts and beneficial delivery of life's raw materials may rarely occur in other planetary systems. Mass extinction events, while devastating, appear to have accelerated evolutionary innovation by eliminating dominant species and creating ecological niches for new adaptations. The 5 major extinctions in Earth's history each preceded periods of rapid diversification and increased complexity. Without these catastrophic resets, life might have remained locked in simpler forms. The evolution of eukaryotic cells required an extraordinarily unlikely endosymbiotic event where one microorganism permanently incorporated another, creating organelles like mitochondria and chloroplasts. This cellular complexity enables the energy budgets necessary for large active organisms. The rarity of successful endosymbiosis might explain why most worlds with life remain microbial. Atmospheric composition represents another critical constraint. Earth's atmosphere provides the right greenhouse effect to maintain liquid water, protects the surface from ultraviolet radiation through ozone formation, and maintains sufficient pressure for liquid water stability. Small changes in atmospheric chemistry could render the planet uninhabitable for complex life. Recent discoveries of extremophile organisms in Earth's most hostile environments have expanded our understanding of life's limits, but they have also revealed how specialized the conditions for complex multicellular life actually are. While microbes might survive in almost any environment with liquid water, the energy requirements and environmental stability needed for large organisms impose much stricter planetary constraints. The search for extraterrestrial intelligence has evolved dramatically since Frank Drake's pioneering Project Ozma in 1960, when he first pointed a radio telescope toward nearby stars. Today's SETI initiatives employ artificial intelligence, machine learning algorithms, and unprecedented computational power to analyze vast data sets for potential alien signals hidden within cosmic noise. Breakthrough. LISTEN, launched in 2015 with $100 million in funding, represents the most comprehensive search for technological signatures ever undertaken. This project monitors over 1 million nearby stars, scans the galactic plane, and observes 100 nearby galaxies across radio and optical wavelengths. Using facilities like the Green Bank Telescope in West Virginia and Parkes Observatory in Australia, Breakthrough LISTEN processes petabytes of data, searching for patterns that natural phenomena cannot explain. The detection methodologies have expanded far beyond simple radio signal searches. Modern SETI researchers hunt for techno-signatures, artificial modifications to planetary environments that advanced civilizations might create. These include industrial pollutants in exoplanet atmospheres, artificial lights on planetary night sides, and massive engineering projects that create regular dimming patterns around host stars. The James Webb Space Telescope has revolutionized our ability to analyze exoplanet atmospheres through transit spectroscopy. When planets pass in front of their stars, starlight filtering through their atmospheres reveals chemical compositions with unprecedented precision. JWST can detect water vapor, methane, carbon dioxide, and potentially artificial compounds that might indicate technological civilizations. Tabby's star, officially designated KIC 8462852, captured global attention when the Kepler Space Telescope observed irregular dimming patterns that defied conventional explanation. While natural phenomena like dust, clouds, or comet swarms likely explain these observations, the star demonstrated how astronomical surveys might detect megastructures like Dyson swarms, collections of solar collectors that could harness stellar energy. The search for optical techno-signatures has identified several intriguing candidates. Fast optical pulses, infrared excess from stellar engineering projects, and unusual spectral lines might indicate alien technology. Ground-based surveys like the Automated Planet Finder at Lick Observatory continuously monitor thousands of stars for brief laser flashes that could represent interstellar communication attempts. Gravitational wave detectors like LIGO and Virgo have opened entirely new observational windows. While these instruments primarily detect black hole and neutron star mergers, they might also reveal signatures of exotic propulsion systems or massive engineering projects involving the manipulation of space-time itself. Advanced civilizations might communicate through gravitational wave modulation or use controlled gravitational anomalies for interstellar travel. The emerging field of astrobiology combines multiple disciplines to understand life's requirements and potential prevalence. The discovery of extremophile organisms in Earth's most hostile environments has expanded the definition of habitable zones, suggesting that subsurface oceans on moons like Europa, Enceladus, and Titan might harbor microbial life. These findings increase the probability that life exists elsewhere, while highlighting the challenges of detecting it. Machine learning algorithms now analyze SETI data with superhuman pattern recognition capabilities. These systems can identify subtle regularities in radio signals that human researchers might miss, while filtering out terrestrial interference and natural astronomical phenomena. As artificial intelligence capabilities advance, these tools may finally detect the elusive signals that have evaded decades of traditional analysis. Future space telescopes promise even greater sensitivity to potential biosignatures and technosignatures. The proposed HABEX and LUVOIR missions would directly image Earth-sized exoplanets, analyzing their atmospheric compositions and surface features. These observations might reveal seasonal changes indicating vegetation, atmospheric oxygen from photosynthesis, or artificial modifications suggesting technological activity. The development of interstellar probe missions like Breakthrough Starshot could provide direct observations of nearby star systems within decades. These gram-scale spacecraft, propelled by laser arrays to 20% of light speed, would reach Proxima Centauri in approximately 20 years, potentially imaging any planets and searching for signs of life or technology. Quantum communication technologies might revolutionize interstellar messaging. Quantum entanglement could enable instantaneous communication across galactic distances, though current physics suggests this requires previously established quantum channels. Advanced civilizations might employ quantum networks invisible to electromagnetic searches, but detectable through quantum interference effects. The resolution of the Fermi Paradox carries profound implications for humanity's future. If we discover that advanced civilizations are common but remain hidden, it suggests cosmic communities await our technological maturation. If the great filter lies ahead of us, understanding these challenges becomes crucial for species survival. If we are truly alone, the responsibility for spreading life and intelligence throughout the cosmos falls entirely upon human shoulders. The next few decades may finally answer Enrico Fermi's haunting question. As our detection capabilities expand exponentially and our understanding of planetary systems deepens, we approach the threshold where the continued absence of alien signals would itself become significant evidence about the nature of life and intelligence in the universe.